Thanks for joining me for MTI's Whiteboard Wednesdays. I'm Dan Adams. Today we're talking about direct drive, linear, and low force friction welding and the differences of each. Today we're going to talk about direct drive, linear, and low force friction welding. In a previous episode we talked about how direct drive was the foundation of all the friction welding processes, and I want to highlight that again today as we extend it into linear and into low force. If you recall, direct drive friction welding, we're attaching a round component on the spindle side and a stationary component on the tailstock side. We rotate it up to a certain speed, and then we bring on a different load profile in order to get the energy in to make the weld. My second load allows me to get some upsetting, and then I squeeze out all the hot material in the forge phase. I can extend this second friction phase where I'm getting upset in order to be able to add more heat to the component so that I can control the cooling rate of it and not form martensite for a hardenable material. I can take that same thought process and apply it to linear friction welding. Now, linear friction welding is, instead of having a rotary motion, I now have an oscillatory motion. So I designate that with a frequency and an amplitude. You can see that I can go through the same load profiles with respect to generating upset. And the reason that I'd use linear friction welding is so that I can oscillate an odd-shaped component and make a weld between that odd-shaped component, being the airfoil in this case, and the disc. Now, the aerospace people who are doing that blisk welding have figured out that, like inertia welding, I can bring on a full forge load from the beginning and I don't have to go through these profiles. I can shorten the weld time, which is a benefit from a metallurgical standpoint, as long as I have enough power in my oscillator to not stall due to the motion. Now, both of these are, again, allowing me to adjust the energy input so that I can generate a weld profile that is attractive for the application that I'm welding. So we took that same thought process and extended it to what we call low force. In low force, we're using an external energy source to add heat while I'm not moving. So I get a preheat before motion starts, whereas in these other two technologies, I'm only generating heat while I'm moving and applying load. Here I can get heat into the component ahead of time, so I can shorten the weld time and need less motion in order to reduce the cost of the equipment. I can also generate that heat while I'm moving, so I can add that external energy as a supplement to the frictional heat that I'm going to generate. And then at the end of the process, I can also have a post-heat phase where I can add energy in order to control the cooling rate, again, so that I don't form martensite and can control the cooling rate of a hardenable material. That helps get the fatigue performance that we need, but I can do it with a faster cycle time at a lower cost compared to what I had to do in direct drive. And here's an example of welding a couple solid bars with low force. Now, what we did was we did this with a linear motion. We can also do this with a rotary motion, but I'm adding energy to this before I start motion, and then I am generating the upset that I need much more quickly. And then because this was a hardenable steel, we control the cooling rate of it, and I avoid forming martensite. The nice thing is that MTI handles direct drive friction welding, we do linear friction welding, and now we also do low force friction welding as an improvement on the previous and traditional friction welding technologies, so that we can custom design the application that suits your part to get the greatest results. Thank you for joining us for this episode of MTI's Whiteboard Wednesdays. For more information on this topic or other friction welding solutions, please visit our website at mtiwelding.com.